Ancient stonework achieves a perfection that defies all logic. We are looking at the precision stone cutting that should have been impossible with bronze tools. Massive blocks of granite, harder than steel, were shaped and fitted together with a seamlessness that challenges our entire understanding of ancient engineering. By the end, you will possess a new framework for judging history's greatest architectural puzzles. How did builders carve mountains into flawless geometry using only soft metal chisels? And what does a cut stone from 1,000 years ago know that our modern tools have forgotten? The mystery forces us to question not just how they built, but what we have lost about the potential of human hands. What does true mastery look like when it leaves no tool behind? The evidence is carved into the very stones themselves. In Egypt, the pyramids are not just mountains of rock, they are assemblies of precision. The granite blocks forming the king's chamber, for instance, are not merely stacked. Their surfaces are ground so flat, so perfectly matched, that the joints between them are often thinner than a sheet of paper. You cannot slide a credit card between stones that weigh more than a modern truck. This is not rough construction, it is fine craftsmanship on a colossal scale. Travel across the world to the high Andes of Peru, and the story repeats with a different alphabet of stone. The walls of Sacsayhuamán or the foundations of Machu Picchu display a similar, breathtaking mastery. Enormous blocks of granite and diorite, some with 12 distinct angles, are locked together in a three-dimensional puzzle. The fit is so intimate, so exact, that after centuries of earthquakes, not a blade of grass can grow between them. The stones hold each other up through geometry alone. And this presents us with the core contradiction, the heart of the mystery. The official historical narrative tells us the builders of these sites primarily used bronze tools. Bronze is an alloy of copper and tin. It is a wonderful metal for many things, but in terms of hardness, it is fundamentally soft. You can scratch it with a modern steel knife. The stones they were shaping, however, granite and diorite, are among the hardest materials on the planet. They are far harder than bronze. Try to carve a block of granite with a copper chisel, and you will not get a precise cut. You will get a blunt, deformed tool and a few shallow scratches. The physics are stubbornly clear, so we are left staring at an outcome that seems to deny its own means. How do you achieve micrometer-level flatness on a 70-ton block using tools that are softer than the material you are working? It is like trying to carve a diamond with a stick of butter. The precision we observe simply should not exist if our understanding of their technology is complete. This is not a minor gap in the historical record, it is a chasm. It forces a profound question. Did these ancient cultures possess a method, a lost technique, that allowed them to work stone with an ease and accuracy we have not yet rediscovered? Or does their achievement point to a different kind of knowledge altogether, one where the relationship between the craftsman, the material, and the tool was something more than we currently comprehend? The stones stand as a silent, persistent challenge, asking us to look again. The traditional explanation is a simple one, a toolkit we can picture in a museum. Builders would have used copper and bronze chisels, struck with stone hammers to fracture the rock along a line. They employed bronze saws, their teeth likely embedded with abrasive sand to help with the cutting, and simple bow drills with copper tips to bore holes. This was a technology of immense patience and effort, perfectly suited for working softer stones like limestone or sandstone. Yet when we apply this same toolkit to the granite of the king's chamber or the diorite of an Andean wall, the logic begins to fracture. The issue is not one of effort but of fundamental material science. To understand why, we need a simple scale of hardness. Imagine trying to scratch one material with another. A fingernail cannot scratch glass, but a diamond can cut glass easily. Geologists use the Mohs scale to measure this property, ranking minerals from 1, like talc, to 10, like diamond. On this scale, copper sits at about a 3. Bronze, being harder, might reach 4 or 4.5. The stones chosen for these precise works, however, granite and diorite, are packed with minerals like quartz, which scores a 7 on the Mohs scale. This is not a small difference, it is a vast gulf. A bronze tool is fundamentally softer than the stone it is trying to shape. In practice, this means a bronze chisel striking granite would not carve it. It would blunt itself, its edge folding over after just a few strikes. The tool becomes the victim of the work. You could use an abrasive like quartz sand between a bronze saw and the granite, and the sand would slowly grind the stone. But this process is incredibly slow, generates a massive amount of slurry, and most critically, it is a blunt, imprecise method. It is like trying to file an intricate key using only coarse sandpaper. You might remove material, but controlling the final shape to a perfect, flat plane with tight seams is another matter entirely. The rapid dulling of tools presents another relentless problem. A crew would spend more time resharpening and recasting their bronze implements than actually cutting stone. So we are left with a vivid disconnect. The standard Bronze Age toolkit explains how you might quarry a massive block or rough out a shape, but it struggles profoundly to explain the final stage, the act of finishing those multi-ton blocks to a flawless, glassy smoothness, of cutting intricate angles and joints that fit without mortar. The tools we attribute to them seem woefully inadequate for the precision we observe. This mismatch is the seed of the mystery, forcing us to wonder if the story we tell about their capabilities is missing a crucial chapter. This precision is not a vague impression, it is a measurable fact. Take the fabled casing stones of the Great Pyramid. Originally, the entire structure was sheathed in brilliant white Chora limestone, but beneath that layer, the core masonry includes enormous granite blocks. The surfaces of these granite blocks are not merely flat to the eye, they are flat to a degree that startles modern stonemasons. When examined with precision instruments, these ancient surfaces show a deviation of less than 1/100th of an inch over an area several feet across. That is a level of flatness comparable to a modern optical workbench, achieved on stone weighing tens of tons. The joints between such blocks are not filled with mortar, they are direct stone-to-stone contact. In many cases, the seam is so exceptionally tight that not even a razor blade can be inserted. This is not a result of settling over time. It is the original condition of the build, a testament to a finishing process of almost unimaginable accuracy. Move from the deserts of Egypt to the mountains of Peru, and you find a different expression of the same principle. The polygonal masonry of the Inca, seen at sites like Ollantaytambo or the base of the Coricancha in Cusco, takes precision into the third dimension. Here, builders used stones with multiple sides, some with 12 or more distinct angles. Each face of one stone had to be cut to match perfectly with the complex, corresponding faces of its neighbors. The result is a wall where every block is a unique, interlocking piece of a massive stone puzzle. There is no standard shape, no simple repetition. Each stone was individually tailored to fit its specific spot with such intimacy that the walls became monolithic in their strength, resisting earthquakes for centuries. This achievement speaks to more than just careful hammering. It implies a sophisticated, perhaps even mathematical, understanding of solid geometry and spatial measurement. The builders were not just stacking rocks, they were solving a continuous, three-dimensional fitting problem with immovable, irregular pieces that weighed many tons each. This evidence pushes the mystery beyond simple curiosity. The perfect flatness, the seamless joints, the complex polygonal fits, these are not decorative flourishes. They are functional engineering feats, A perfectly flat surface distributes weight evenly, preventing stress points. A tight joint without mortar makes a structure more resilient to seismic shifts. The interlocking shapes create a wall that moves as one unit. The precision we admire is fundamentally the signature of a deep, applied knowledge. It shows a culture that did not just move mountains, but conversed with them in the language of geometry and physics. The stones themselves are the blueprint for a lost school of practical knowledge, asking us how such flawless execution emerged from a toolkit that, by our current understanding, seems fundamentally unsuited to the task. Faced with this undeniable precision, historians and archaeologists propose a compelling first answer. Perhaps the ancients did use bronze and copper, but not in the way we initially imagine. Their secret weapon may not have been the metal itself, but what they combined it with. This theory centers on the clever use of abrasives, essentially turning ordinary sand into an invisible blade. Think of it not as cutting the stone, but slowly, meticulously grinding it away. The process is surprisingly straightforward in concept. A craftsman would use a simple copper saw, a flat sheet of metal without sharp teeth. Between this saw and the granite block, he would pour a wet slurry of quartz sand and water. Then, with a team pulling the saw back and forth, the hard quartz particles in the sand, which are tougher than the granite's feldspar and mica, would become embedded in the soft copper. The copper blade essentially becomes a carrier for millions of microscopic cutting teeth. Each stroke drags these ultra-hard quartz grains across the stone's surface, grinding off a tiny, almost imperceptible amount of material. It is a testament to immense patience, but it works. The same principle applies to drilling. A hollow copper tube rotated with a bow drill and fed with abrasive slurry could core a perfect cylinder out of solid granite. The evidence for this is etched into history itself. In the ancient Egyptian quarries at Aswan, the famous Unfinished Obelisk still lies in its bedrock, providing a frozen snapshot of this technology. Around its base, archaeologists have found clear, parallel grooves cut into the granite. These grooves match the width of a copper saw and are filled with a residue of quartz sand, the literal dust of the operation. Here, the theory moves from speculation into the physical record. The marks left behind align perfectly with a process of abrasive sawing. This method elegantly solves the hardness problem. It does not matter that the copper is soft because the copper is not doing the cutting. It is merely the vehicle. The real work is done by the abrasive, a material harder than the stone itself, which is abundantly available in the surrounding desert. It transforms the impossible into the merely labor-intensive. This explanation feels satisfying, a brilliant adaptation within known technological limits. It showcases human ingenuity, making a profound result from simple, available components. Yet, as we lean into this answer, a new set of questions quietly emerges. While abrasive sawing can explain how a block was separated from the bedrock, or how a large stone might be trimmed down, does it fully account for the final, breathtaking finish? Can the process of dragging a slurry-covered copper sheet produce the optical flatness, the perfectly planar surfaces, and the complex, multi-angled joints we see in the finest works? The grinding action is inherently somewhat random, as individual sand grains fracture and move, achieving a surface flat to within 1/100th of an inch across several feet might require another level of control, a finishing technique that goes beyond the abrasive saw. The theory provides a crucial piece of the puzzle, a believable method for the bulk of the work, but the final whisper of perfection on the stone suggests there might have been one more step, a secret touch in the final act of creation that has since faded from memory. Yet the story of ancient stonework is not one of a single secret, but of a symphony of techniques. Beyond the clever use of abrasives lies a second category of explanation, one that relies not on hidden technology, but on profound mechanical understanding and immense, sustained human effort. These methods are sophisticated in their simplicity, turning basic physics into a precision instrument. One of the most elegant examples is the use of wooden wedges to split stone. This technique works with the material, not against it. Craftsmen would first identify a natural floor line or grain in a granite outcrop. Along this line, they would drill a series of holes using those abrasive-tipped drills. Then they would drive dry, hardwood wedges into each hole. The final act was to soak the wedges thoroughly with water. As the wood absorbed the water, it expanded with tremendous, relentless force. This expansion, channeled along the line of holes, would create a clean fracture, splitting a massive block free from the bedrock with a startling degree of control. It was a patient application of natural force, a collaboration between human intention and the properties of wood and stone. Once a rough block was liberated, the shaping began. Here, we encounter one of the most physically demanding tools imaginable, the dolerite hammerstone. Dolerite is a volcanic rock that is even harder than granite. Ancient masons would use fist-sized or larger pieces of dolerite, holding them in their hands and pounding directly onto the surface of the granite block. With each strike, a small amount of the granite would pulverize into dust. This is not a delicate process, it is a monumental exercise in persistence. The evidence is written across countless unfinished stones and quarry sites, a landscape of characteristic pockmarks, a dimpled texture left by millions of precise, careful blows. Imagine the sound, the rhythmic percussion echoing for years as a rough block was slowly, methodically beaten into a smooth plane. This pounding technique, while brutal in its expenditure of labor, could be guided to produce remarkably flat surfaces. By working systematically across the stone and using straight edges or taut strings as guides, skilled workers could essentially grind down the high spots until the entire face met the desired plane. The final smoothing might then be achieved by rubbing with finer stones or abrasive sands, moving from the macro to the micro scale of finish. When we combine these methods, the picture becomes one of staggering, coordinated effort. Wooden wedges for quarrying, dolerite hammers for rough shaping, abrasive sands for cutting and drilling, and finally, meticulous hand polishing for the last perfect surface. It is a toolkit of sheer willpower, measurement, and time. Theoretically, with enough skilled labor, enough patience spanning generations, and a rigorous tradition of geometric knowledge passed from master to apprentice, such techniques could inch toward the precision we marvel at today. The walls would rise not from a magic tool, but from a culture that elevated stonework to a supreme discipline, where the lifetime of a craftsman was a worthy investment for a joint that would last 1,000 years. This explanation honors the human element, the bone-deep effort behind the beauty. Yet, even as we acknowledge this incredible feat of endurance, a quiet question lingers at the edge of the pounding sounds. Does the sheer scale of the labor fully account for the mathematical perfection we see? Could repetitive pounding, even guided by strings, produce surfaces flat to 1/100th of an inch across their entire expanse? Or does the flawless geometry hint at a guiding principle, a final step in the process that ensured not just flatness but perfect conformity? The answer may lie not in how they hit the stone, but in how they knew when to stop. But the sheer magnitude of the work defies easy comprehension. Let us take the dolerite hammerstone method and apply it to a single, modestly sized granite block for one of the pyramid's interior chambers. To shape just one surface of a block measuring, say, 6 feet by 4 feet, using only pounding stones, would require an almost unimaginable number of strikes. Each blow from the hard dolerite would remove only a tiny chip or a puff of dust. To reduce the surface by even 1 inch across that entire area, you might need hundreds of thousands of deliberate, controlled impacts. Now consider that the block has 6 sides, all needing to be shaped and made perfectly perpendicular to one another. The process for that single block could consume months of labor for a dedicated team. And then you must multiply that effort by the thousands upon thousands of blocks that constitute a major pyramid or temple complex. The logistical scale becomes staggering. Where did the armies of skilled workers live, and how were they fed? How was the immense supply of hammerstones, which themselves wore down quickly, sourced and managed? The coordination required moves from impressive to nearly superhuman. The abrasive sawing method, while clever, introduces a different kind of constraint: time. Cutting through granite with a copper blade and sand is a glacially slow process. Experiments have shown it might progress at a rate of only a few millimeters per hour. To saw a block free from bedrock or to trim it to a precise dimension could take weeks or even months of continuous, back-breaking work for just one cut. When you layer this slow, meticulous technique over the entirety of a monumental project, the timeline suggested by conventional history begins to feel impossibly tight. Could a society using these methods have completed structures of such scale and perfection within the reign of a single pharaoh or ruler, as some records imply? The consistency of the work adds another layer of mystery. The precision is not an occasional flourish on a prized block. It is the standard, repeated thousands of times over. This suggests an organized, repeatable industrial process, not just heroic individual effort. How did they maintain such uniform quality across decades of construction and across generations of craftsmen? The pounding method, reliant on human muscle and judgment, would naturally introduce variations, yet the stones tell a different story, one of near-perfect conformity. This forces us to weigh two possibilities. Either these ancient societies commanded labor forces and logistical networks so vast and efficient that they could brute force their way to geometric perfection, an achievement in social organization that is itself a profound mystery. Or there is a missing element in our understanding of their process, a technique or tool that increased efficiency and ensured consistency, allowing them to achieve with 100 workers what we might think would require 10,000. The stones do not just ask how they were cut, they ask how it was done with such breathtaking speed and unwavering accuracy. Perhaps the most telling clues are not in the walls but in the holes left behind. Deep within the ancient Egyptian quarries and on the faces of finished monuments, we find evidence of a drilling technology that seems to defy its own simplicity. Archaeologists have recovered numerous core samples, cylindrical plugs of stone that were drilled out of solid granite and basalt blocks. These are not crude, jagged holes. They are smooth, perfectly round cylinders, and their surfaces tell a story written in stone. When examined closely, the sides of these cores reveal fine, continuous spiral grooves running from one end to the other. The pattern is consistent and uniform, like the rifling inside a gun barrel. This is a critical detail. These spiral grooves indicate the path of the drill bit as it ate its way into the impossibly hard rock. The consistency of the groove, its unbroken spiral, suggests a feed rate, the speed at which the drill advanced, that was remarkably steady and controlled. The official explanation aligns with the abrasive theory. It proposes that ancient workers used hollow tubes of copper, fixed to a spindle that was rotated by a bow or a team of people. Abrasive sand mixed with water would be fed into the hole. As the tube spun, the sand particles trapped between the copper and the granite would grind away a circular channel. Over time, the tube would sink deeper, leaving behind a solid stone core inside it. Eventually, the core could be broken free and removed, leaving a clean, cylindrical hole. In theory, this method works. Experiments have replicated it, producing similar cores with spiral markings. The abrasive does the cutting, and the copper tube is just a guide. Yet when engineers and machinists look at the ancient cores, some raise an eyebrow. The spiral grooves on the best examples are not just present, they are exceptionally uniform. The spacing between each groove is nearly identical along the entire length of the core. This kind of consistency is difficult to achieve with a purely manual process. Imagine trying to drill into granite by hand with a bow drill. Your speed would vary with every pull, your pressure would waver as your arms tired. The resulting spiral groove would be irregular, with sections that are tighter or wider apart. But the finest ancient cores show a feed rate that implies a constant downward pressure and a remarkably stable rotational speed. This is the kind of precision we associate with a machine tool, something that applies force evenly and turns without interruption. Could a team of workers, no matter how disciplined, achieve such mechanical perfection through muscle power alone? The depth of some drill holes adds to the puzzle. Some examples penetrate deep into the stone, requiring a drill bit or a copper tube that remain true and straight over a long distance. Maintaining perfect alignment in a deep hole with a hand-powered tool is a tremendous challenge. Any wobble or variation in pressure would cause the drill to bind or the core to fracture. This evidence sparks a quiet but persistent debate. One side argues for the supreme skill of the ancient craftsman, suggesting that generations of practice led to techniques that could mimic machine-like consistency. Perhaps they used weighted guides to ensure steady pressure, or a team of workers rotating the drill with a flywheel to maintain a smooth, even spin. The other side looks at the evidence and wonders if we are missing a component. Could there have been a form of mechanical assistance, a simple but effective machine that provided a constant feed and a stable rotation? Something as straightforward as a weighted lever system for pressure, or a capstan turned by oxen to rotate the drill, could transform the process from a feat of endurance into one of controlled engineering. The cores sit silently at the center of this debate. They are not just waste products, they are fossilized recordings of a process. The unbroken, even spiral is a fingerprint, and it asks us whether we are hearing the rhythm of human hands or the faint, forgotten echo of an ancient machine. The granite itself holds the memory of its own shaping. On the edges of cut blocks and within the trenches of ancient quarries, we find the ghostly signatures of the saws that made them. These are not random scratches, but clear, parallel striations running along the surface of the stone. They are the permanent tracks left by the cutting tool, a fossilized record of its passage. The pattern is often remarkably consistent, a series of straight lines running side by side. This simple fact is the starting point for a surprisingly complex debate. The official explanation points back to the abrasive slurry method, a long copper blade, perhaps manned by teams of workers pulling back and forth, would have quartz sand constantly fed beneath it. As the blade moves, the hard sand grains are dragged across the granite, each one grinding a tiny, linear groove. Over thousands of strokes, these individual grooves merge into a flat surface, and the parallel striations we see are the cumulative effect of this abrasive grinding action. It is a logical and demonstrable process. Experiments using reconstructed copper saws and sand have successfully cut granite, leaving behind similar striation patterns. The evidence seems to align perfectly, yet when we look closely at the scale and precision required for some of the most monumental cuts, questions of practicality arise. Consider the task of sawing a granite block that is 10 or 15 feet long. To achieve a perfectly straight, planar cut across that entire distance using a flexible copper sheet and manual labor is an immense challenge. Any variation in pressure, any slight bend or twist in the blade, would cause the cut to wander, creating a curved or uneven surface. The parallel striations on some of the finest cuts, however, are not just present, they are exceptionally uniform and straight over the entire length. This suggests a sawing motion that was not only consistent in its back and forth path, but also held in a rigid, perfectly aligned plane. Could a team of workers, pulling on ropes attached to a long, flimsy copper blade, maintain such flawless mechanical stability for hours or days on end? The depth of some cuts adds another layer to the mystery. Some saw marks penetrate several inches into solid granite. maintaining the alignment and pressure on a deep cut becomes exponentially more difficult as the blade can bind or deflect within its own channel. The parallelism of the striations on opposite sides of a deep cut would be especially hard to preserve. This has led some researchers to propose an alternative idea. Perhaps the sawing apparatus was not just a simple sheet of metal pulled by hand. What if it incorporated a form of guidance, a simple wooden frame to hold the blade perfectly rigid, or a system of weights and pulleys to ensure a constant, even pressure on the abrasive slurry could transform the process? Such a device would not require advanced metallurgy, just a clever application of leverage and stability. It would be a machine in the truest sense, a tool that enhances control and repeatability. The problem is that no such guided sawing apparatus has ever been found in the archaeological record of these Bronze Age cultures. We have the copper, we have the stone with the marks, but we lack the intermediate technology that might bridge the gap between brute force and flawless execution. This absence is not proof of anything, of course. Wooden frames and rope rigging decay to dust, leaving no trace after millennia. The silence of the archaeological record can be misleading. So we are left weighing two possibilities, each with its own implications. The first is a testament to supreme human skill, where generations of craftsmen developed a feel for the stone and a coordinated rhythm so perfect they could mimic the precision of a machine with their hands and eyes alone. The second possibility hints at a modest but profound mechanical ingenuity, a forgotten class of simple machines that provided the stability needed for such perfect cuts. Both paths lead to the same stunning result, a seam in the stone so straight and true it has lasted for ages. The saw marks are not just lines, they are a question etched in granite, asking us to decide where the boundary lies between human artistry and the quiet assistance of a guiding hand. The spiral grooves on a drill core record motion, but the perfect flatness of a finished block captures something more profound, a state of being. It is one thing to cut a stone, but another entirely to know when it is truly flat, or when two faces meet at a perfect right angle. This is the quiet genius of the craft, the invisible geometry that gives the stone its silent strength. Without laser levels or digital theodolites, how did an ancient mason establish a reference plane across a block longer than a bus, or ensure that the corner of a foundation was exactly square? The answer likely lies not in complex machinery, but in the elegant application of simple physics. Think of a water level, one of humanity's oldest and most reliable tools. It is nothing more than a length of hose, open at both ends and filled with water. Yet the water, seeking its own level, will always settle at exactly the same height in each end, regardless of the distance between them or the uneven ground beneath. By marking this water line at multiple points around a massive stone slab, builders could transfer a perfectly horizontal plane across any distance. It is a tool of beautiful simplicity, immune to the sagging that affects a taut string over long spans. For establishing vertical lines and right angles, the tools were equally straightforward. A simple frame, a wooden triangle with a plumb bob hanging from its peak, could be placed against a stone face. When the bob's string aligned with a mark at the frame's center, the leg of the frame was perfectly vertical. Two such verified vertical lines set at a corner could define a perfect right angle. Taut cords rubbed with colored dust and snapped against a surface would leave a perfectly straight guideline for cutting or dressing the stone. The principles are elementary, but their consistent application across a project of thousands of stones is where true mastery resided. The deeper challenge, however, is one of verification over scale. You can use a water level to mark points around a single block, but how do you ensure that this block's surface is perfectly coplanar with the next block 10 feet away and the one after that across an entire wall 50 feet long? One compelling theory suggests the use of master reference stones. Imagine a single, exquisitely finished slab of granite, its surface ground to an ultimate flatness. This would become the primary standard, the sacred template of true flatness for the entire worksite. Craftsmen could use this master stone to check and true their simpler tools, like long, straight edges made of wood or stone. They would rub the edge of a working stone with a colored pigment, then press the master straight edge against it. The high spots on the working stone would pick up the pigment, showing the mason exactly where more grinding or pounding was needed. This process, repeated with infinite patience, would slowly propagate that original standard of perfection from the master stone to every block in the structure. It is a method of quality control that is both humble and brilliant, ensuring that every piece, no matter who shaped it or when, would conform to the same invisible ideal. The possibility that such a reference system existed hints at a sophisticated organizational mind behind the hammer blows. It suggests a culture that understood the concept of a calibrated standard and the need to preserve it across time and space. The real mystery, then, may not be the initial creation of a flat surface, but the system that ensured that first perfect plane was copied, again and again without degradation until the final stone was laid. That system, a blend of simple tools, rigorous process, and guarded knowledge, might be the true lost secret, the silent discipline that turned a mountain into a mirror. The final perfect surface is only half the story. Once a block of granite was cut and polished to a flawless plane, it faced a perilous journey. Transporting a 70-ton stone across miles of desert or up the steep slopes of a mountain, and then lifting it into position high on a rising wall, presented a second monumental challenge, one where a single misstep could shatter weeks of meticulous craftsmanship. How do you move a masterpiece without leaving a scratch? The theories for moving these colossal weights are familiar in broad strokes, yet each step in the process had to be executed with a care that bordered on reverence for the precision already achieved. The most likely method involved a combination of brute force and elegant physics. Giant wooden sledges, likely lubricated with water or a slick slurry of mud, could distribute the stone's immense weight. Teams of workers would pull with ropes, perhaps guided by a foreman beating a rhythm on a drum to coordinate their efforts. To ease the sled's path, workers might place wooden rollers or a track of greased timbers underneath it, effectively creating a primitive but effective railroad for a single, priceless cargo. Levers, simple poles of hard wood, were the fine adjustment tools. A crew could insert levers under one edge of the sledge, using smaller stones as fulcrums, to make minute corrections in direction or to gently nudge the block the last few inches into its final position. Ramps built of earth, brick, and rubble provided the sloping highways to lift stones to ever greater heights. The engineering of these ramps was itself a feat, requiring stable construction to support constant, heavy traffic. Yet here we encounter the subtle complication introduced by precision. A block with edges sharp enough to produce a paper-thin joint is also fragile. Banging such a stone onto a wooden sledge or letting it grind against a misplaced roller could chip a critical corner, ruining the perfect fit. The transportation process, therefore, had to be as controlled as the cutting process. The sledges likely had padded beds or were designed to cradle the stone securely. The transition from rollers to final placement would have been a delicate ballet of levers and measured force, not a rough shove. This logistical symphony, the coordinated pull of hundreds, the steady roll of timbers, the whispered instructions as levers took the strain, was all in service of preserving an invisible quality. It was not enough to get the stone to the wall. It had to arrive in the same pristine condition it left the mason's yard. This adds a profound layer of respect to our understanding of these projects. The care invested in the stone did not end when the last abrasive grain was washed away. That care was woven into every step of its journey, a protective custody that lasted until the moment it clicked silently into place, finding its forever home in a wall built to outlast the ages. The true monument was not just the final structure, but the sustained intention that carried each perfect piece from quarry to sky. Yet the sheer difficulty of these traditional methods has fueled a persistent, more speculative line of inquiry. What if the ancient builders possessed a different kind of knowledge entirely, one that changed the stone itself? This idea moves beyond tools of force and into the realm of chemistry. Some researchers propose a theory that seems pulled from alchemy, the notion of stone softening. Imagine a plant-based paste or a chemical agent derived from local herbs or minerals that could be applied to the surface of granite. This substance, according to the theory, would temporarily alter the crystalline structure of the rock, making it pliable, almost like wet clay. In this softened state, a worker could mold, carve, or stamp the stone with relative ease, achieving complex shapes and perfect fits. After a period of time, the chemical would dissipate, and the stone would re-harden to its original, formidable strength, locking the form in place forever. This would elegantly explain the seamless joints and the lack of tool marks on certain surfaces. It would transform an act of brutal labor into one of applied science. Proponents of this idea sometimes point to legends and fragmented accounts from various cultures that speak of liquids or plants that could melt stone, suggesting a distant memory of a lost technique. Another variation of this chemical approach is the geopolymer theory. This suggests that some of the stone blocks, particularly the limestone casing of the pyramids, were not quarried at all, but cast in place using an ancient form of concrete. The idea is that the builders crushed softer limestone, mixed it with a natural binder like kaolinite clay and a reactive silica from ash or natron, and poured this slurry into wooden molds. As the mixture cured, it would chemically reconstitute into a synthetic stone, indistinguishable from natural limestone. This could explain the perfect fit of certain blocks, as a poured material would naturally conform to the shape of its neighbor. Mainstream archaeology, however, views these theories with profound skepticism. The critique is rooted in a fundamental principle of the field, the need for evidence. To date, no chemical analysis of the stone from these precise monuments has revealed a residual agent that would indicate a softening process. No historical text from the builders themselves, in their detailed records of materials and methods, describes such a technique. No archaeological dig has uncovered a vessel, a workshop, or a residue that conclusively points to the manufacture or use of a stone softening compound or a geopolymer formula for structural blocks. The geopolymer theory, while intriguing for some applications, faces its own material challenges. The granite and diorite used in the most precise works are igneous rocks, formed under immense heat and pressure. Reproducing their complex crystalline structure and mineral composition through a casting process, especially on the scale of multi-ton blocks, is a problem modern materials science has not solved. The critique is not meant to stifle imagination, but to anchor it in the verifiable. Archaeologists argue that the absence of evidence, when combined with the abundant evidence for the labor-intensive methods we have discussed, makes the chemical theory an extraordinary claim that currently lacks its own extraordinary proof. It places a sophisticated chemical industry in the ancient world for which no infrastructure has been found. So we stand at a crossroads between two very different visions of the past. One is a story of supreme skill, patience, and the brilliant use of simple physics. The other is a story of lost science, a forgotten recipe that made the impossible easy. Both seek to answer the same silent question from the stones. Beyond the realm of chemistry lies an even more ethereal possibility, one that speaks to a harmony between builder and material. What if the secret tool was not a chisel or a chemical, but a carefully sustained note? This speculative theory suggests that ancient cultures might have harnessed the power of sound, vibration, and resonant frequency to influence solid stone. The idea draws from a fascinating principle in physics. Every object has a natural resonant frequency, a specific pitch at which it vibrates most easily. Apply that precise frequency with enough energy, and you can induce powerful vibrations within the material itself. In theory, if you could find and amplify the resonant frequency of a granite block, the intense, focused vibrations might cause the crystalline structure to temporarily become less rigid, even to the point of appearing malleable or fluid. Proponents of this acoustic theory imagine a scene where priests or technicians used massive tuning forks, specially shaped chambers, or arrays of chanting voices to project these frequencies onto a stone. The vibrating block, now in a state of internal agitation, could then be shaped or molded with reduced physical force, its particles seemingly dancing into a new form. Once the sound ceased, the stone would settle, locking its new shape with perfect precision. This could explain the surreal, melted appearance of some stone joints and the seemingly impossible curves found in certain ancient architecture. It is a concept that bridges the gap between monument and melody, suggesting a lost science where architecture was a form of frozen music. It must be stated clearly that this remains a fringe theory, a captivating idea born from the depths of the mystery itself. To date, there is no archaeological evidence, no ancient sonic tools, no inscriptions describing acoustic levitation, no physical residue of such a practice that provides empirical support for its use in monumental stonework. Mainstream science has not replicated the effect on the scale required for multi-ton construction, yet its persistence in speculative discussion is telling. It represents the outer boundary of our imagination when confronted by the silent perfection of the stones. When logical, labor-based explanations feel stretched to their limit, the human mind seeks more elegant, almost magical solutions. The sound theory, while unproven, serves a vital purpose in this exploration. It demonstrates the profound impact this ancient mystery has on us. It shows that we are not just looking for lost tools, but for a lost relationship with the material world, a connection so profound it feels like it must have been orchestrated by forces we can barely perceive. The stones compel us to consider every possibility, from the sweat of the hammer to the potential song of the cosmos, in our quest to understand their origin. The stone vessels present a different kind of mystery entirely. In the storerooms of museums, you can find containers carved from hard stone like diorite and granite, dating back thousands of years. Their exteriors are often beautifully shaped, but it is their interiors that stop modern machinists cold. Some of these vessels have been hollowed out with necks narrower than the body, creating an undercut, a shape that seems impossible to achieve with a simple hand drill. The inner surfaces are frequently perfectly symmetrical, with smooth, consistent curves that appear to have been turned on a lathe. The symmetry is so precise, so mechanically even, that it whispers of a rotating tool. Could these artifacts be the physical evidence of ancient machining? The idea is compelling. Imagine a simple rotary lathe powered by a bow or a foot treadle, with a stone vessel fixed to a spindle. As it spins, a fixed cutting tool, perhaps tipped with a harder abrasive stone, could be brought to bear, shaving the interior into a flawless, symmetrical form. This would explain the uniform curves and the undercuts, which a handheld tool would struggle to produce without leaving telltale wobbles or irregularities. Proponents of this theory often point to the famous Unfinished Obelisk in Aswan as further, larger-scale evidence. The trenches cut around that giant stone are clean, straight, and parallel, suggesting the use of a guided cutting apparatus that moved in a consistent plane, something beyond a team of men with handheld saws. The suggestion is that a culture capable of such precision on a small scale, with lathe-turned vessels, might have scaled that knowledge up, using large, perhaps water or animal-powered machinery to dress the faces of monumental blocks. It is a vision of an industrial past, humming with the forgotten sound of rotary motion. The orthodox archaeological perspective offers a different interpretation, one rooted in demonstrable skill rather than speculated machinery. Experts point out that the symmetry in stone vessels could be achieved through a process called pecking and grinding. A craftsman would first rough out the interior with a hard stone hammer, then use a shaped grinding stone attached to a wooden rod. By spinning the rod back and forth between the palms or using a bow to rotate it and constantly feeding an abrasive slurry, a patient artisan could slowly, over hundreds of hours, wear the interior into a smooth, symmetrical shape. The consistency comes from the constant rotation of the grinding head and the unchanging shape of the tool, not from spinning the vessel itself. It is a testament to the human capacity for repetitive perfection. As for the obelisk trenches, the parallel saw marks are seen not as proof of a machine guide, but as evidence of a highly disciplined workforce using long, straight reference cords and the established abrasive sawing technique. The straightness is a product of meticulous marking and controlled effort, not necessarily of mechanization. This debate sits at the heart of our struggle to understand the past. One view looks at the artifact and sees a product that, to our modern eyes, implies the technology we know can make it. The other looks at the same artifact and sees the pinnacle of what dedicated human hands, armed with simple principles and boundless time, can achieve. Both require us to expand our understanding, either of ancient capability or of human potential. The vessels and the quarry marks do not provide a final answer. They simply hold the question up to the light, asking us to decide where we draw the line between the artisan and the machine, and whether that line might have been drawn in a different place long ago. Perhaps the most profound tool was not held in the hand but held in the mind. The breathtaking precision we see in stone may be less about the force applied and more about the knowledge that guided it. This suggests a deeper layer to the mystery, one rooted in intellectual mastery. The seamless joints and perfect planes could be the physical expression of a culture that saw the world through geometry and the stars, a society where building was a sacred act of aligning human creation with cosmic order. Their measurement systems were likely derived from astronomical observation, creating units that were not arbitrary, but reflections of celestial cycles. This provided a stable, repeatable foundation for all their work. When every length is a fraction or a multiple of a cosmic constant, consistency becomes embedded in the very blueprint of thought. Planning a structure of such scale required more than a rough sketch in the sand. It demanded advanced surveying to lay out perfectly square foundations over uneven terrain, a task that implies a sophisticated grasp of trigonometry long before it was formally defined. The Great Pyramid's near-perfect alignment to the cardinal directions is not a lucky accident. It is an achievement of observational astronomy, requiring the ability to track stars with enough precision to establish true north, east, south, and west. This celestial knowledge was then translated down to the ground, likely using simple tools like gnomons or shadow sticks to map the heavens onto the earth. The geometry did not stop with orientation. The proportions of the pyramids themselves often encode mathematical constants, like the ratio of a circle's circumference to its diameter. While debates continue about the intentionality of these relationships, their potential presence hints at a world where number, shape, and form were deeply interconnected. A builder who thinks in terms of perfect triangles and sacred ratios does not settle for a roughly squared block. The intellectual framework demands a physical perfection to match the purity of the idea. This perspective shifts the mystery from a question of how they cut the stone to how they knew what to cut. The flawless flatness of a surface becomes a testament to their ability to conceive of and insist upon a perfect plane. The intricate polygonal joints of the Inca walls reflect a three-dimensional spatial reasoning of the highest order, solving complex fitting problems that would challenge a modern architect. The stone, in this light, is not just material, it is the canvas for applied mathematics. This intellectual mastery provided the invisible template. It told the mason not only where to strike, but when to stop, because the ideal form, derived from geometry and the cosmos, was the ultimate guide. The pounding of dolerite hammers or the grinding of abrasive sand was the physical orchestra, but the symphony was composed by astronomers and geometers. Their knowledge provided the unwavering standard against which every block was judged, ensuring that a project spanning generations remained faithful to a single, perfect vision. This suggests that the true lost secret might not be a tool of metal or a recipe for softening stone, but a way of thinking, a cultural discipline that merged the practical with the profound, turning construction into a ceremony of precision that honored the very order of the universe. But what if our entire timeline is misplaced? The stones themselves might be whispering a different story, one that begins long before the pharaohs we credit. This line of inquiry challenges the very foundation of history, suggesting that some of these precise structures could be far older than conventional archaeology accepts. The most famous argument for this revised chronology centers on the Great Sphinx of Giza. Geologists examining the iconic statue have pointed not to its form, but to the patterns etched into its limestone body. The erosion on the Sphinx and the walls of its surrounding enclosure, they argue, shows deep, vertical, and undulating channels. This specific weathering pattern, according to some geologists, is characteristic of prolonged, heavy rainfall water erosion, not wind and sand. The last period when the Giza Plateau experienced such a consistently wet climate was at the end of the last ice age, around 9,000 to 11,000 years ago. If the erosion is primarily from rainwater, then the Sphinx, and perhaps the core structures around it, could be millennia older than the reign of Pharaoh Khafre, to whom it is traditionally attributed. This would place its construction in a prehistoric era, a time before dynastic Egypt, potentially by a culture or civilization now lost to time. Proponents of this view suggest such a precursor society might have possessed a different technological paradigm, one that could explain the precision we struggle to understand with Bronze Age tools. They point to other global anomalies like the megalithic foundation at Göbekli Tepe in Turkey, dated to over 11,000 years ago, as evidence that sophisticated stoneworking emerged much earlier than our textbooks state. This revised timeline offers a seductive solution. It neatly sidesteps the tool problem by suggesting the work was done not with bronze, but with a different, perhaps now vanished, technology from a forgotten age. The mainstream scholarly consensus, however, remains firmly anchored in the established Bronze Age timeline. Egyptologists counter that the geological evidence is not so clear-cut. They argue that other factors, like the effects of groundwater capillary action, the chemical dissolution of limestone from morning dew and salt crystallization, or even the weathering from wind-driven sand and occasional torrential downpours in later periods, could produce similar erosion features. They emphasize that there is no archaeological evidence, no tools, no settlements, no cultural layers at Giza that date back to that prehistoric wet period. All the material evidence, from pottery shards to worker settlements, consistently points to the Old Kingdom. The dating is further supported by historical context, artistic style, and the alignment of the structures with the constellations as they appeared in the 3rd millennium before the Common Era. To move the timeline requires dismissing a vast, interconnected web of archaeological findings in favor of a single, interpretative line of evidence. The debate is a powerful reminder of how we reconstruct the past. One side listens to the stone itself, reading its physical biography in cracks and channels. The other side listens to the totality of the human record, the artifacts and writings left behind. Both are trying to hear the same truth, but they are listening for different frequencies. Whether the Sphinx holds the memory of a lost reign or not, this challenge to chronology forces a valuable question. It asks us to consider how fragile our historical narratives can be, built as they are on layers of interpretation. And it wonders if we have misjudged the age of the mason. Could we have also misunderstood the nature of his tools? The theories are compelling, but the ultimate test lies in the hands of modern craftsmen. Experimental archaeology takes these ideas from the page and puts them to work in the real world with stone, copper, and sweat. Teams of researchers and skilled stonemasons have dedicated years to attempting what seems impossible, replicating the ancient precision using only the tools and materials believed to be available. One of the most famous endeavors was led by a man named Roger Hopkins, a stonemason who collaborated with an Egyptologist on a major television project. Their goal was to cut a piece of granite using a replica copper saw and abrasive sand. The team constructed a large wooden frame to hold a 6-foot-long copper blade, and teams of workers pulled it back and forth for hours each day, constantly feeding a slurry of sand and water into the cut. The process was agonizingly slow, but it worked. After many days of relentless labor, they successfully sawed through a modest-sized granite block. The experiment proved the fundamental feasibility of the abrasive method. The saw marks left on the granite were strikingly similar to those found on ancient stones. This was a significant victory for the traditional view, demonstrating that the basic technology was indeed capable of separating hard stone. Yet, even in this success, the limitations of the method became vividly clear. The cut was not perfectly straight or planar over its entire length. It had a slight curve, a wandering path that reflected the challenge of maintaining perfect alignment with a flexible blade pulled by human hands. Achieving the flawless flatness of a pyramid block would require an additional, meticulous finishing process after the sawing was done. Other experiments have focused on the pounding technique. Modern masons using dolerite hammerstones have shown they can shape granite. The process is brutally physical, a symphony of constant, ringing impacts. One mason described it as not so much cutting the stone as persuading it, blow by tiny blow, to surrender its form. Through immense patience, they can produce flat surfaces and even complex shapes. The time investment, however, is staggering. Shaping a single block to a high degree of precision could take a small team many months. This raises the profound question of scale. Could an entire civilization, even with a large labor force, have produced thousands of such perfect blocks within the timeline suggested by history using only this method? The experiments suggest it is technically possible, but they stretch our understanding of ancient logistics to its absolute limit. The most telling outcome of these hands-on trials is not a simple yes or no. Instead, they reveal a spectrum of possibility. They confirm that the ancient toolkit was sufficient for the quarrying, the rough shaping, and the basic cutting. Where the experiments often reach their boundary is in that final whisper of perfection, the last 1% of accuracy that transforms a well-made block into a geometric marvel. This gap points not to a missing technology, but perhaps to a missing layer of skill, a cultural mastery of technique that took a lifetime to learn and was passed down through generations of dedicated artisans. The stones from these modern experiments are impressive, but they are not the equals of their ancient counterparts. They stand as respectful tributes, proving the path was walkable, while quietly acknowledging that the ancient builders walked it with a grace and speed we are still struggling to fully comprehend. This missing layer of skill might be the most powerful technology of all. We are accustomed to a world where precision is born from machines, from digital readouts and computer-guided cutters. It is easy to forget that the human hand and eye, trained over a lifetime, can become instruments of astonishing accuracy. The real secret behind the ancient stone may not be a forgotten tool, but a forgotten kind of craftsman. Imagine a society where the highest calling was not to be a king or a warrior, but a master mason. From childhood, an apprentice would be immersed in the craft. His first years would be spent mixing abrasive slurries, fetching water, and observing. He would learn the feel of different stones by hand, the sound a dolerite hammer makes when it strikes granite correctly, and the subtle visual cue that reveals a hidden flaw in the rock. This was not a job, it was an identity passed from one generation to the next. The knowledge was not written in books but in muscle memory and practiced ritual. A master could judge flatness by running his palm over a surface and feeling the slightest whisper of a ridge. He could sight down a length of cord and know if it deviated by the thickness of a thread. This level of sensory refinement is almost unimaginable today, but in a culture dedicated to monumental, sacred construction, it was the essential technology. The perfect joint was not an accident, it was the inevitable product of a tradition that allowed no compromise. Each master mason was the living repository of centuries of trial and error, of tiny improvements passed down and perfected. A slight change in the angle of a hammer strike, a new method for securing a guide cord, a better recipe for an abrasive paste, these incremental advances, honed over generations, could accumulate into a capability that looks like magic to an outsider. The culture itself was the engine. When an entire society's spiritual and political power is invested in building monuments meant to last for eternity, the resources follow. The most talented individuals are directed into the crafts. The state provides food, housing, and materials. A project becomes the work of a lifetime, not a rushed contract. In this environment, time ceases to be a pressing constraint in the way we think of it. Taking a year to perfect a single block is not inefficiency, it is devotion. This changes the equation completely. What seems impossibly laborious to our modern, efficiency-obsessed perspective was simply the expected pace of creation. The workforce was not an anonymous mob, but a structured hierarchy of specialists, quarrymen, rough dressers, fine masons, and master installers, each with deep expertise in their single step of the process. This division of labor, fueled by cultural purpose and sustained by tradition, could achieve a consistency and quality that rivaled machine production. The stones, then, are not proof of a lost device, but of a lost discipline. They are the legacy of a human technology where skill was so deeply cultivated that it became a natural force, as capable of shaping mountains as any machine we have since invented. We search for a tool in the dirt, but the greatest tool may have been the culture that shaped the minds and hands of those who held it. Yet this legendary precision was not the standard for every wall and building. The evidence itself presents a crucial, often overlooked distinction. The most astonishing examples of seamless joints and optical flatness come overwhelmingly from royal tombs, state temples, and sacred monuments. These were the prestige projects of their age, funded by the entire treasury of a kingdom and blessed with the patronage of gods and pharaohs. They received not just the finest materials, but the absolute pinnacle of human skill and attention. For every perfectly fitted granite block in the king's chamber, there are countless other stones from the same era that tell a different story. Look at the foundations of ordinary houses, the walls of provincial granaries, or even the lesser pyramids built for lower-ranking officials. The stonework here is competent, sturdy, but often visibly rougher. The joints are wider, filled with mortar. The surfaces are not glassy smooth, but show the clear marks of tools and a more pragmatic approach to construction. This contrast is not a contradiction, it is a revelation. It tells us that the so-called impossible precision was not an everyday technology, nor was it a secret known only to a lost civilization. It was instead the highest possible achievement of the existing technological toolkit, pushed to its absolute limit by a concentration of will and wealth. It was the difference between a standard family car and a hand-built Formula One racing machine. Both operate on the same basic principles of internal combustion and engineering, but one represents an extreme, specialized application of those principles, where cost is no object and the goal is perfection. The political and economic will was the essential catalyst. A pharaoh could command the labor of thousands, could divert the nation's best artisans from all other projects for a lifetime. and could afford the immense wastage of material that such meticulous work inevitably entailed. An ordinary citizen building a home could not. This selective application of precision helps resolve part of the mystery. It shows that the capability was there within the known technological framework, but it was so extravagantly expensive in terms of time, labor, and resources that it was reserved for the most spiritually and politically significant endeavors. The ordinary stonework acts as the control in our historical experiment. It shows us what the baseline Bronze Age technology looked like when applied without the overwhelming force of a state's entire focus. The legendary monuments, in turn, show us what that same technology could produce when pushed by a culture's ultimate ambition. They are not proof of a forgotten science, but of a forgotten scale of commitment. The real wonder, then, may not be how they cut the stone, but what they were willing to sacrifice to make the cut perfect. Modern technology is now turning its gaze back toward these ancient surfaces, reading them with a new kind of vision. Researchers employ high-powered microscopes and three-dimensional laser scanners to analyze the microscopic topography of tool marks, searching for the unique signature left by each method. This is not guesswork, it is forensic archaeology, examining the crime scene of creation to identify the weapons of construction. The scans create digital maps of stone surfaces with a resolution finer than a human hair, revealing the direction, depth, and pattern of every microscopic groove and scratch. What these high-tech investigations often reveal is a remarkable consistency that supports the traditional abrasive theory. The striations on many cut surfaces show the characteristic parallel, slightly wavy pattern of a back and forth sawing motion, with evidence of embedded abrasive particles. The spiral grooves on drill cores display the variable pitch and occasional irregularities one might expect from a hand-powered rotation, not the perfect uniformity of a modern machine tool. In many cases, the microscopic evidence aligns beautifully with what experimental archaeology has demonstrated, showing that the known toolkit of copper, sand, and dolerite hammers could indeed produce the marks we see. This data provides powerful, empirical support for the narrative of immense human skill. Yet, even within this confirmation, subtle anomalies sometimes appear. On certain exceptionally flat surfaces, the microscopic tool marks are not just uniform, they are nearly absent, polished away to a degree that suggests a final finishing process of extraordinary finesse. Some scans of complex polygonal joints reveal that the mating surfaces are not just flat, but slightly convex, a sophisticated technique that actually creates a stronger, more stable lock than two perfectly flat planes. This is not a mistake, it is advanced engineering, a detail invisible to the naked eye but revealed by laser light. Other analyses of saw cuts show a consistency in the width and depth of striations over very long distances, a steadiness that again raises the question of guided control versus freehand work. The technology does not always provide a single, definitive answer. Instead, it deepens the conversation, adding layers of nuance. It confirms the fundamental soundness of the abrasive and pounding techniques, while simultaneously highlighting the pinnacle of skill required to execute them so flawlessly. The data tells us that the known methods were sufficient, but it also quantifies just how masterfully they were applied. The mystery thus evolves. It shifts from a simple question of capability to a more profound appreciation of execution. We are left not wondering if they could do it, but how they could do it with such relentless, repeatable perfection, achieving a standard that modern scans show to be geometrically exceptional. The stones are no longer silent, they are speaking in a language of microns and vectors, and what they are describing is a level of craftsmanship that continues to command our deepest respect. The truth likely lies somewhere between these two compelling stories. On one end of the spectrum rests the abrasive and patience model, a narrative of supreme human effort. It is a story we can see, touch, and even replicate. The quarry marks the pounded surfaces, the successful modern experiments, all form a strong, evidence-based chain of logic. This view presents ancient builders not as possessors of magic, but as masters of their material world, using simple physics, immense coordination, and generational dedication to push their known toolkit to an absolute extreme. The precision becomes a monument to cultural will, a society's collective decision to invest lifetimes in perfecting a single stone for a purpose greater than themselves. It is a profoundly human explanation, one that honors the bone-deep skill we know our ancestors possessed. At the other end of the spectrum glimmers the lost technology model, a narrative of forgotten knowledge. It is driven by the lingering anomalies, those specific details that feel like stubborn outliers, the machine-like consistency of some drill cores, the optical flatness on a massive scale, the seemingly impossible internal symmetry of certain stone vessels. These are the pieces that do not snap neatly into the patient labor puzzle. They whisper of a possible efficiency, a guiding principle, or a subtle technique that has since faded from the record, leaving behind only its perfect products as a taunting clue. This view appeals to our sense that history is full of gaps, that civilizations rise and fall, taking their secrets with them. It suggests that our current understanding of the past may be incomplete, that a chapter on practical stoneworking genius might have been lost. Weighing these against the full body of evidence, a balanced picture emerges. The great majority of the work, the quarrying, the moving, the rough shaping, and likely the majority of the finishing, is convincingly explained by the known techniques executed at a level of skill and scale that still staggers our modern imagination. The cultural and logistical framework of these societies provided the engine, and the simple tools provided the means. Yet, hovering at the very edge of this achievement are those specific artifacts, those perfect seams and inexplicable symmetries that continue to resist a full and comfortable explanation. They are the exceptions that prevent the case from being completely closed. They are the quiet, persistent questions that the stones continue to ask, ensuring that the mystery, while diminished, remains partially and tantalizingly alive. Perhaps the deepest reason this mystery resonates so powerfully is that it touches a quiet fear in our modern soul, the fear of forgetting. We live in an age of exponential technological accumulation, where knowledge is stored in clouds and progress is measured in ever faster processes. We assume history is a straight line, a steady climb from simple tools to complex machines. The flawless stone cuts stand as a stark, silent rebuke to that comforting narrative. They suggest that progress is not always a forward march. It can be a spiral where certain peaks of practical skill, of a deep, tactile understanding of material, are reached and then, for reasons we may never fully know, abandoned. The knowledge of how to achieve that specific perfection with those specific tools was not stored in a book or a blueprint. It was stored in the hands, eyes, and communal traditions of the artisans. When that culture shifted, when its priorities changed or its institutions faded, that granular, embodied knowledge could evaporate within a few generations. It is a humbling reminder that our own technological civilization, for all its data backups, is not immune to loss. What core understandings might we, in turn, be forgetting? The stones challenge our arrogance. They ask us to consider that an ancient mason with no digital calipers might have possessed a faculty of judgment and a quality of attention that we, surrounded by assisting machines, have allowed to atrophy. This is not about ancient astronauts or lost super science. It is about recognizing a different kind of intelligence, one rooted in a lifelong, sacred dialogue between a human being and a mountain. The puzzle forces a reconsideration of capability itself. We look at a bronze chisel and see a soft metal, a master craftsman steeped in a tradition stretching back centuries might have seen in that same chisel a partner in a delicate dance with abrasive sand, knowing exactly how to tilt it, how much pressure to apply, and how to listen to the sound it made against the grain of the granite. His capability was not in the tool alone, but in the centuries of refined technique that the tool represented. This shifts our perspective from what they had to who they were. It suggests that the true engine behind these wonders was a cultural environment that could produce individuals and collectives of such extraordinary skill that their work appears miraculous to us. The mystery, therefore, is not ultimately a technical one. It is a human one. It invites us to expand our definition of advancement. A society can be advanced in its social organization, in its artistic vision, in its cultivation of specialized crafts, and in its spiritual commitment to a project, even if it does not possess the steam engine or the semiconductor. The silent, perfect walls are a testament to that broader, richer kind of advancement. They do not simply ask how this was done. They ask us what we value, what we are capable of dedicating ourselves to, and what fragile masteries we might be overlooking in our relentless pursuit of the next new thing. In the end, the greatest lesson from the stones may be a lesson in humility, and a quiet encouragement to look at the past not as a primitive prelude to ourselves, but as a gallery of different and in some ways unparalleled human achievements. This realization carries a weight far greater than any single tool. If the ancient builders truly achieved their legendary precision with the simple toolkit we attribute to them, then the story we must tell about them changes in a fundamental way. It becomes less about a search for lost gadgets and more about an awe-inspiring portrait of human society operating at its peak. The true marvel shifts from the potential of a machine to the potential of a civilization. Consider the sheer coordination required to shape, transport, and place thousands of multi-ton blocks with such flawless consistency demands a social machine of breathtaking complexity. It speaks to a society capable of long-term planning across generations, of feeding and housing vast workforces, of training artisans from childhood in a sacred craft, and of maintaining a unified vision that outlasted any single ruler's life. This is not merely construction, it is the ultimate expression of social cohesion and shared purpose. The mathematical knowledge implied is equally profound. Achieving optical flatness and perfect alignments over vast distances required more than a good eye. It demanded a rigorous, practical understanding of geometry, proportion, and measurement. Their ability to translate celestial alignments onto the ground, to lay out perfectly square foundations on uneven terrain, and to maintain those standards for decades reveals a culture that thought in terms of pure form and cosmic order. The stones are their frozen equations, but perhaps the most humbling implication is for the artisan. This view elevates the individual craftsman from a laborer to a master of a lifetime's discipline. It suggests a level of cultivated skill so deep that the hand and eye could rival the precision we now outsource to digital guides. Imagine the sensory knowledge required to feel the truth of a surface with a palm, to hear the correct pitch in a hammer strike, to judge a right angle by the shadow of a chord. This was a knowledge written in muscle memory and patience, a technology of the human body and mind refined over centuries. Framing the accomplishment this way makes it, in many respects, more impressive than if we discovered they had a power tool. A machine can be found, reverse-engineered, and understood. A cultural achievement of this magnitude is far more elusive and profound. It represents the summit of what human beings can do when a society aligns its resources, its intellect, and its spirit toward a single, monumental goal. The pyramids, the perfect walls, the seamless joints, they are not just tombs or temples. They are the physical evidence of a civilization's highest priorities, a testament to what they believed was worth 1,000 lifetimes of effort. This reframes our entire relationship with the past. We are not looking back at primitive people who needed a secret to succeed. We are looking back at masters who succeeded with what they had, to a degree that still defines the limits of our imagination. Their legacy is not a puzzle to be solved with a single missing piece, but a mirror held up to our own assumptions about progress, skill, and what it means to build something meant to last forever. The most honest witnesses are often the projects left incomplete, scattered across the ancient world, frozen in the very act of creation, like quarries and building sites abandoned mid-task. These places are not failures, they are time capsules, offering an unfiltered glimpse into the workshop of history. The most famous is the Unfinished Obelisk, still lying in its granite bed in Aswan, Egypt. If completed, it would have been the largest single piece of stone ever quarried by the ancients, towering over 100 feet tall. Its sides are partially freed from the bedrock, and the trench around it is a textbook of ancient technique. The parallel grooves lining the trench walls are the clear, straight marks of abrasive saws, exactly as the conventional theory predicts. More tellingly, at the base of the trench, archaeologists found the actual residue of the work, a gritty powder of quartz sand, the very abrasive used to grind through the granite. This site powerfully validates the abrasive method as a primary technology for separating colossal stones. Yet, look closer at the obelisk itself. Along one of its upper edges runs a series of deep, rounded channels. These are not saw marks, but the distinctive pock marks left by teams of workers pounding the stone with dolerite hammerstones, trying to undercut it from below. Here, in one location, we see two different methods employed simultaneously: the precise sawing for defining straight edges and the brute force pounding for bulk removal. It is a snapshot of a multi-stage process, a blend of techniques tailored to the task. Travel to the Andes, to the quarries that supplied the stones for sites like Ollantaytambo. Here, among the scattered blocks, you find stones caught in various stages of preparation. Some are rough, freshly split from the bedrock with visible wedge holes. Others show the characteristic dimpled texture from extensive pounding with hammerstones. A few display remarkably straight, incised lines, grooves cut into the surface as guide marks for the masons. These guidelines are not random, they are precise, often forming perfect right angles or outlining the complex polygonal shapes the stone was destined to become. This tells us the shaping was not a free-hand endeavor. It began with careful measurement and marking, a geometric plan transferred directly onto the raw stone. The presence of these guidelines, alongside the hammering evidence, supports a narrative of meticulous, planned labor rather than a mysterious softening or molding process. The stones were not being made pliable, they were being persuaded, blow by controlled blow, to conform to a pre-drawn design. Perhaps the most revealing evidence of all comes from the mistakes. In the walls of Sacsayhuamán, you can find a handful of stones that do not fit perfectly. One famous example is a block with a protruding knob that was never fully dressed down, leaving a small gap in the joint beside it. This mistake is incredibly informative. It shows that the perfect fit was achieved by custom shaping each block to its neighbors, a trial and error process. The masons would likely rough shape a block, attempt to fit it, then identify the high spots preventing a tight seal. They would mark those spots, remove the block, and carefully pound or grind away only the marked areas before trying again. The block with the knob represents a point where this process was interrupted, perhaps due to time, shifting priorities, or a decision that the fit was good enough for that particular location. This single imperfection reinforces the human, hands-on nature of the work. It argues against a process that produced perfect fits in one attempt, like a casting or a molding technique might. Instead, it shows a gradual, iterative refinement, the signature of a craftsman solving a physical puzzle in real time, with stone and patience as his only tools. These unfinished sites and errors form a powerful counter-argument to the most exotic lost technology theories. If the builders possessed a chemical agent that could soften stone, why would they spend weeks pounding a trench around the unfinished obelisk with hammerstones? Why would they leave the clear, laborious marks of abrasive sawing and pounding all over their quarries? If they were using advanced sonic levitation or machine tools, why would guide lines for hand shaping be so carefully etched into the rock? The fossilized work sites overwhelmingly present a picture of immense, coordinated human effort employing the simple, physical methods we can identify. They show the expected stages from quarrying with wedges to rough shaping with hammerstones to precise finishing with abrasives and guided saws. The evidence in the stone is consistent, repetitive, and speaks the language of gradual mastery, not sudden magic. This does not diminish the accomplishment, it grounds it in a reality we can comprehend, even if we still struggle to fathom the scale of the perseverance it required. The abandoned projects are the ultimate testimony, not to how the work was meant to end, but to how it truly began. Our modern gaze often sees the past through a lens of mechanical limitation. We unconsciously equate true precision with the hum of a laser cutter or the digital readout of a milling machine, believing that such accuracy simply could not exist before the industrial age. This assumption creates a subtle but powerful bias, a filter that makes ancient achievements appear impossible by default. The very phrase, "impossible with bronze tools," reveals this bias, framing the entire mystery around what they supposedly lacked rather than what they demonstrably possessed. But if we look beyond stone, we find a world filled with pre-industrial precision that challenges this narrow view. Consider the wooden joinery of a master shipwright from the Age of Sail. Without a single nail or modern adhesive, they would carve complex, interlocking joints, dovetails, mortise and tenons, scarfs, that fit together with such airtight perfection that the hull would be both flexible and watertight, capable of weathering ocean storms. This was not achieved with computer-aided design, but with a lifetime of cultivated skill, an intuitive understanding of grain and stress, and tools no more complex than a hand saw, a chisel, and a mallet. The precision was in the craftsman's hands and eyes, honed by tradition and relentless practice. Look to the metalworkers of the Renaissance, who forged intricate suits of plate armor. These were not crude shells of iron, but finely articulated sculptures of steel, engineered to allow a nightful range of movement. The curved plates had to be shaped with such exacting conformity to the human body that they distributed impact and avoided pinching. The rivets and hinges moved with smooth precision. This metalworking marvel was achieved with hammers, anvils, forges, and files. It was a precision born of iteration, of shaping, testing, and refining, of knowing the metal so intimately that the smith could feel its resistance and potential in every strike. Or consider the navigators who crossed vast oceans using little more than the stars, a compass, and a crude sextant. Their challenge was one of angular precision, of measuring their position on a featureless globe with astonishing accuracy. They succeeded not with GPS satellites, but with meticulous observation, detailed charts, and mathematical tables painstakingly calculated by hand. These examples are not anomalies, they are testaments to a different kind of technological sophistication. They prove that human ingenuity, when channeled through deep expertise and supported by a culture that values a craft, can produce results that border on the miraculous, even with simple tools. The common thread is not a secret device, but a profound depth of knowledge embedded in the muscles, in the community, and in the slow, cumulative advances of a tradition. When we confront the perfect stone joints of antiquity, perhaps we are not seeing a technological gap, but a gap in our own understanding of what dedicated human skill can accomplish. We search for the machine in the workshop, but we should be searching for the lifetime of learning in the mind and hands of the artisan. The stones do not defy the laws of physics, they defy our modern expectations about the limits of pre-industrial hands. This reframing is crucial. It moves the mystery from the realm of lost super science to the realm of human potential, a potential that history shows us time and again is far greater than we often assume. The debate ultimately leaves us not with a solved equation, but with a profound appreciation for the depth of the question itself. A definitive, universally accepted answer may forever remain just out of reach, and this elusiveness is perhaps the most telling part of the mystery. The complete context of the artisan's world, the rhythm of their daily practice, the unspoken tricks of the trade passed from master to apprentice, the very feel of the tools in their hands, is a dimension of knowledge that has faded with the sound of the last hammer strike. We are left with the magnificent results, but the intimate process, the lived experience of achieving that perfection, is lost to time. This is why the mystery persists with such quiet power. It resists closure not necessarily because of one spectacular missing technology, a single magic key, but more likely due to a combination of factors we struggle to weigh accurately from our distant vantage point. It was the perfect alignment of optimized, simple techniques, applied with a level of skill we can barely quantify. It was the immense, focused resources of a civilization pouring its collective will into a sacred project. And above all, it was a cultivated mastery, a deep, intuitive conversation between human intelligence and the natural world, that we, in our age of machine-assisted precision, have yet to fully replicate or even completely comprehend. The stones do not whisper a secret formula, they echo a forgotten standard of what human hands, guided by an unwavering cultural purpose, were once capable of achieving. So the stones remain, and with them the quiet echo of a question. The precision stone cutting of the ancient world stands not as a riddle to be solved once and for all, but as a permanent testament to the boundless reach of human ingenuity. Whether we see in these seams the ultimate expression of known methods, pushed to a breathtaking extreme by cultural will and generational skill, or we sense the faint outline of a lost nuance, a forgotten trick of the trade, the achievement itself is undeniable. It challenges the comfortable, linear story we often tell about progress. It asks us to look at a bronze chisel and see not a limitation, but a key that unlocked a discipline we have since misplaced. This is the enduring power of such historical puzzles. They do more than spark curiosity about the past. They hold up a mirror to our present assumptions. They force us to wonder what we might be underestimating in our own ancestors, and by extension, in the latent potential of focused human effort. The allure is not in finding a single magic answer, but in the sustained conversation between the evidence and our imagination. As we walk away from these silent, perfect walls, we are left with a final, lingering thought. If our understanding of something as tangible as stone and bronze can contain such depth and debate, what other capabilities of ancient cultures are we only beginning to glimpse? What other chapters of human skill and intellect, written not in books but in the landscape itself, are waiting for a fresh perspective, a new question, or a humble acknowledgement that the past may still have much to teach us about the art of the possible?